Hello people around the world, ever wondered where's the current between the plates of the capacitor? Like if you see here, there is current in this region of the circuit, there is also current in this part of the circuit. But what happens to the current between the plates of the capacitor? Now this discontinuity was a mystery to the scientists over the years, and this mystery was solved in the 19th century, and yes, we are going to discuss the solution today. First of all, let's think about it naively. Okay, so what is current? Current is basically flow of charges, right? And if you see over here, capacitor is a device which stores charges, right? It does not let the charge flow between the plates of the capacitor. So there is no flow of charge between the plates of the capacitor, hence no current. Or are we missing something? The story begins in 1831 with a great scientist and experimentalist, Michael Faraday. So in 1831, Michael Faraday was performing an experiment, and this is the modified version of his experiment. Okay, so he actually performed the experiment with two coils, but here for understanding purposes, I have chosen a magnet, a coil that is connected to a galvanometer. Okay. So galvanometer is basically a device that detects current. Okay, so whenever there is current in the circuit, there is a needle in the galvanometer which is going to deflect. Okay, the needle deflects in the presence of the current. Okay, so whenever there is current flowing in the circuit through the galvanometer, the needle will deflect, and that will indicate the presence of current in the circuit. So galvanometer is a device that detects current. Okay, so now let's come back to the experiment. What did Faraday do? Faraday just moved this magnet around this coil. Okay, and he made an amazing discovery over here. Whenever he moved the magnet around this coil, there was an induced current over here, which means the needle of this galvanometer deflected. Okay, on movement of this magnet, the needle of the galvanometer deflected. So there was a current induced in the circuit due to the movement of the magnet. Now you high schoolers, some of you might know it as Faraday's law of electromagnetic induction, and you say it as an EMF is induced across the coil whenever it is subjected to a changing magnetic field, right? So this is basically the Faraday's law, and the EMF, which the voltage which is induced over here due to which the current flows, it is given by minus n d phi by dt. Okay, so not going into the very details of this, so but let's discuss it briefly. Okay, so this is the voltage or the EMF that is created across this coil. Okay, n is the number of turns in the coil. Okay, the number of turns over here, d phi by dt, that is the flux change of the magnetic field. Okay, basically you can see that whenever you bring this magnet closer to the coil, more number of magnetic field lines will pass through it, and when you take the magnet far, lesser number of magnetic field lines will pass, right? So the flux or the number of field lines basically is changing with respect to time, right? So that is basically this term. Okay, the rate of change of magnetic flux. Okay, so n times the rate of change of magnetic flux, that will provide you the EMF, the voltage that is developed across this coil. Okay, and minus sign basically because of Lenz's law, to show that the EMF or the current that is produced in the scenario over here will be of the opposing nature. It will oppose the cause which is causing it. Okay, anyways, let's not get into that. But yeah, this is how you find the EMF, and this is how you learn Faraday's law of electromagnetic induction at high school, right? But in true a sense, Faraday's law of electromagnetic induction is a changing magnetic field produces an electric field. Okay, so a changing magnetic field produces an electric field. This is the true essence of Faraday's law. So basically here we have our moving magnet, right? This is the changing magnetic field we are talking about. Okay, so this when we are moving this magnet, we are creating a magnetic field which is constantly changing, right? So this changing magnetic field will produce an electric field that will move the electrons, and that will make the current flow, right? The electrons are moving, charges are flowing, and that's why current is there in the circuit, right? So a changing magnetic field produces an electric field is the true essence of our Faraday's law. Okay, now Faraday's law was of electromagnetism was a great discovery. He was greatly appreciated for it, and he was asked what good is it, and he just sarcastically replied, what good is a newborn baby? So let's briefly discuss the inconsistency in MPR Circuit Law. Now I know you might feel that we are going tangents today. We were supposed to discuss what happened to the current between the plates of the capacitor, and here we are discussing laws. But I will just say that these are pieces of jigsaw. In the last chapter, all these pieces will come together and that will solve our puzzle. Okay, so hold on till then. Okay, so let's come back over here. So this horrifying thing that you see is nothing but your MPR Circuit Law. Okay, so it's nothing to worry about. Okay, you just picture it this way, that MPR Circuit Law is used to determine magnetic field in a region. Okay, so you basically choose an Amperian loop like I've chosen over here. Okay, you multiply the current enclosed in that loop. You can see the current enclosed over here is I, right? So the current enclosed by that loop is I. You multiply it with a constant mu naught, okay, and that you equate to this thing, and you have to solve this in order to find the magnetic field in that region. So MPR Circuit Law, you just picture it this way, that it is a law that will help us determine magnetic field in an region. Okay, so you make an Amperian loop, you see the current enclosed, multiply it by mu naught, set up this equation, solve it for B. B is basically the magnetic field, and that is the magnetic field in that region. Okay, so here we have our DC voltage source which is connected to a capacitor and then connected to a resistor. Okay, now we have chosen the capacitor in its charging state. Okay, you can see the current is going from here to here, or electrons from this plate are going to this plate. So this plate is becoming more positive and this plate is becoming more negative, or the capacitor is charging up. Okay, so basically here we have chosen this Amperian loop. Okay, you can see that the current enclosed in this Amperian loop is I, so mu naught times the current enclosed, and we have set up this equation, right, from MPR Circuit Law, and we can solve this and we will find the value of magnetic field, right? But that is what we are not going to do. We are going to keep it over here. We know that there is magnetic field in this region, right? If we keep a magnetic needle over here, it is going to deflect. We in fact know it from very long time that current carrying conductors produces a magnetic field around it, right? The right hand rule. Okay, so if this is a current carrying conductor, current is going in the upward direction, so you have magnetic field lines around it, curling around it. Okay, so this is basically the right hand rule, and so there is magnetic field all over here. Okay, so if you place a magnetic needle over here, it will deflect. Okay, so now coming to the interesting part over here. Okay, this is one part, so we know there is magnetic field over here. Now let's choose an Amperian loop which is between the plates of the capacitor. Okay, so we have chosen an Amperian loop which is between the two plates of the capacitor. Okay, again we set up the equation for MPR Circuit Law. Integral BdL is equal to mu naught times the current enclosed in this loop. If you see, this loop encloses no current, right? What is current? Current is flow of charge, right? Charge is not flowing between the plates of the capacitor. Okay, it's stored over there, right? So there is no current flowing between the plates of the capacitor as of now, right? So the current enclosed is 0. This gives you 0 on the right hand side, and when you solve it, you'll get that the magnetic field in this region is 0. But here's the catch. Okay, when we placed our magnetic needle in this region, it deflected. Yeah, it deflected. And this was something which was pointed out by Maxwell, and this showed that MPR Circuit Law is maybe wrong. In fact, our MPR Circuit Law was not completely incorrect. It was just incomplete. So Maxwell, James Maxwell, who had pointed out that there is magnetic field between the plates of the capacitor, he took the responsibility of completing this MPR Circuit Law. So for that, he developed this idea of displacement current. Now he said that in between the plates of the capacitor, we have displacement current. Okay, so he said that there is in fact current between the plates of the capacitor, and he called it displacement current for obvious reasons. One being that it is of the different nature, right? It is not as the same nature as the current we have in the conducting wire. Okay, basically because we have been discussing this from the very start, that your charges cannot flow between the plates of the capacitor, right? So this current does not involve physical flow of charges. It is something hypothetical, but yeah, it completes our MPR Circuit Law. Okay, so here we have displacement current between the plates of the capacitor. Maxwell also obtained this relation that displacement current equals epsilon naught and into the rate of change of the electric flux. Okay, epsilon naught is basically a constant. It is called permittivity of free space. Okay, and this is the rate of change of electric flux. Now the in between the plates of the capacitor, the electric field is constantly changing when the capacitor is charging or discharging. Okay, so we'll come to that in a while, but before that, just cherish this idea that our MPR Circuit Law is finally complete. Okay, now you can see that if we choose our Amperian loop over here outside the plates of the capacitor, this term will be 0, right? Because displacement current is due to fluctuations in your electric field, but outside the capacitor there is no fluctuations in the electric field, so displacement current is 0, this is 0, and this is your MPR Circuit Law as you know it, right? And but if you come in between the plates of the capacitor, okay, now you'll see that this current is 0. This I is basically the conduction current, the conventional current that we all know, the current which is due to the flow of charges, right? This current is 0 over here. Okay, this current is 0 over here, so this term flies off and this term still remains because displacement current has some value now, right? There is fluctuation in electric field over here. Displacement current has some finite value multiplied by some constant, has some value not equal to 0, and the magnetic field now will not be equal to 0 between the plates of the capacitor, which rightly explains why the our magnetic needle deflected between the plates of the capacitor. Okay, so now let's understand. Now our MPR Circuit Law is complete, right? Let's move one step ahead and understand how the electric field between the plates of the capacitor is actually changing. Okay, so for convenience, I've chosen a capacitor which is in the charging state. Okay, so you can see current flowing from here to here, or electrons being moved from this positive plate to the negative plate. Okay, so we can imagine this current flow as small dq charges, right? We can consider this as a small plus dq charge flowing from this plate to this plate, or an electron flowing from this plate to this plate, whatever you want to imagine. Okay, so you can see that after some time the charge density on this plate will increase, right? Plus charge plus dq is being accumulated on this plate, right? So the charge density is going on increasing with time, right? The electric field of capacitor, by the way, if you don't know, is given as charge density by epsilon naught. So we know over here that charge density is increasing, epsilon naught is a constant, which means that your electric field is increasing. In the charging condition, your electric field is constantly increasing, or to say it in general terms, it's changing, right? So there is change in the electric flux, right? So the number of field lines between the plates may increase, will increase in fact, okay, when the charge goes on accumulating. So due to increase in the charge density, electric field goes on increasing, and hence there is a change in the electric field between the plates of the capacitor, and that gives rise to your displacement current. Okay, this was the whole idea. In fact, you didn't need the concept of displacement current. Okay, displacement current was just developed to prove your MPR Circuit Law to be correct. Okay, to complete your MPR Circuit Law. You can also do it without MPR Circuit Law. You can see that here we have a changing electric field, right? So it is well established now that a changing electric field produces a magnetic field. Just like in Faraday's law, a changing magnetic field produces an electric field. Okay, so here from here you could have directly said that a changing electric field produces a magnetic field. So here we have a changing electric field between the plates of the capacitor, which is producing the magnetic field, which is deflecting the magnet of our magnetic needle. Okay, so that is the reason why our needle is being deflected. Okay, why there is magnetic field in that region. So we could have proceeded without the idea of displacement current, but displacement current in a way is a good thing. If you see, it is debunking the discontinuity, right? The discontinuity problem is no more. You can see the current over here. There is also current between the plates of the capacitor now, and there is current after that too, right? And our displacement current is also completing our MPR Circuit Law. By the way, this is Maxwell MPR Circuit Law, right? It had to be. He was the one who proposed the correction, right? So, is there a current between the plates of the capacitor? Apparently, there is, and it's displacement current. And that's the last piece of our jigsaw puzzle today.